Finally going to do something practical with KSP. We're going to learn how to predict something. And I'm going to show you what that something basically is here with the little demonstration that you actually saw once before in Chem 1. All right, using the reaction quotient. Back then, we did not do this quantitatively. All right, well, let me show you what we're going to predict. If I take some saturated potassium sulfate, and I pour it into this graduated cylinder. Okay, this is saturated potassium. You know how you make saturated potassium sulfate. Same way you made your saturated salt solution in lab yesterday or the day before, whenever we did that lab. We're going to do another lab tomorrow. So to make up a saturated solution, you just basically add more of the stuff that can dissolve in water and then pour off the top, decant it. All right, if I pour some of this in here, I'll notice that it's clear because I've got, I poured off the top. Left behind would have been the potassium sulfate that didn't dissolve. Now, right now, there's as much potassium sulfate that could possibly dissolve in there. Now, I'm going to do something. I'm going to add some alcohol to it. Alcohol is by no means as good a solvent for potassium sulfate as water is. So when I add the isopropyl alcohol, which is less polar, all right, not as polar as water is, what happens is it starts to form what? A precipitate. All right, now normally we don't make a precipitate this way. We normally make a precipitate by adding two solutions together that are clear, and then the product that's made is insoluble, and that's what we're going to be doing up here. But this is a cool precipitate because, as you can see, what's it doing? It looks like it's snowing. And you may remember seeing this last year. You may remember seeing this yesterday when it snowed, or the day before, even in April. But basically, I'm making a precipitate. And a lot of times when you make your precipitates, you don't see them like this. You don't see the actual solids. You just see it looks milky. It looks cloudy. All right, but that's a precipitate. Now, what we're going to learn how to do today is predict whether a precipitate forms, not just by looking up on this sheet here like you did last year, if you have soluble or insoluble for the product, but rather actually being able to calculate using KSP whether a precipitate will form based on the concentration, the molarity. All right, and that requires solving for what's called the reaction quotient. All right, the reaction quotient is the same thing as KSP, pretty much the same thing. All right, except it's not necessarily at equilibrium. You may remember doing Q back in the first equilibrium chapter. We did solve for Q back then. And that was going to tell us whether the reaction needed to go forward, reverse, or was at equilibrium when we did it. So now we can actually calculate whether a precipitate forms in terms of its actual concentration. Okay, because what we're going to do is we're going to solve for Q. All right? You're going to take two solutions, two clear solutions. This one's clear beforehand, this one's clear after. You're going to do this in the lab tomorrow. And you've done this 100 times. We've seen a yellow precipitate like that. We've seen white precipitates. We've seen numerous precipitates in Chem 1 and Chem 2. You're going to be able to tell, if you know the concentration of that guy, you know the concentration of that guy, whether you will get a precipitate or not. Okay? All right. And how are you going to do that? Well, if QSP is equal to KSP, you have a saturated solution. It's at equilibrium. It's where it's got as much as could possibly dissolve. It is what the situation I had when it was just this bottle right here. That was saturated. A saturated solution, by the way, will not look cloudy. It will not show a precipitate. However, if QSP is less than KSP, that tells me we're not going to get a precipitate. Why? Because basically, if you remember what Q means, all right, the Q means that the forward reaction has to occur more until it reaches equilibrium, which means more can still dissolve, all right? And if Q is greater than KSP, it means there's going to be a precipitate. Now, you won't always necessarily be able to see that precipitate. The rule of thumb is about 1,000 times greater than Q has to be than K, all right? But we aren't going to worry about that. I'm just going to ask you to solve for Q is either greater than, less than, or equal to, and you'll either tell me whether there's a precipitate formed or not, all right? But it's not quite that simple. The reason we did, several reasons actually, the reason we did that original review day, or 2 days I think of review we did, molarity and dilution. Well, they're going to become important. They've already been important. Many of these problems have asked us, given this many grams, this many milliliters, calculate the molarity. But now, you're going to find that when I mix 2 things together, let's go back for a second. When I mix 2 things together, you realize that if I put 100 milliliters of this into 100 milliliters of that, the concentration of this is no longer what it was once I mix it together. So that's going to be important for these calculations. So that's why we did the dilutions ahead of time, all right, knowing we were going to have to use them in these. All right, so let's do 2 problems. I'm going to do one very easy one. Copy this guy down. This is the easy one. I made the numbers easy and I made the formulas easy in that there's just, you don't understand why it's easy right now, but you'll see it as we're doing the problem. Everything kind of works out and you'll see why. Then I'm going to do a harder problem, which has 2 twists to it. And I'll show you a little trick to take care of one of the twists at least. All right, so I'm asking if a precipitate is going to form. If I take 100 milliliters of 0.001 molar Na2SO4, sodium sulfate, and add it to 100 milliliters of barium chloride. That's 0.01 molar. Now, if you were to just write out the equation for sodium sulfate plus barium chloride yields barium sulfate plus sodium chloride, you would predict that a precipitate forms. But the question is the concentration strong enough to see that precipitate? Will it form? All right, or is the concentration, not high enough to actually show that? And these are very low concentrations, I mean 0.001. And when I add them together, what am I going to do to each of those? They're going to be even less because they're going to dilute them. Okay, so basically, small numbers like this, you don't really know if you're going to see a precipitate or not. Let's take a look at what we have to do. Well, the first thing we're going to do is we'll write the equations for the solubility of each of these guys, and we'll put their new concentrations in. Now, I made this first one easy. If I have 100 milliliters of that, add it to 100 milliliters of that, what's going to happen to the concentration of each of these guys? They're going to be cut in half. Everybody see why? All right, makes sense. 100 milliliters to 100 milliliters. And by the way, a lot of people don't understand this. As a matter of fact, the first question, 27, came up. It doesn't matter that it's not 100 milliliters of water. It could be 100 milliliters of anything is going to dissolve it. Whether it's 100 milliliters of this solution or not, it just changed the volume by that much. So let's look what happens when sodium sulfate dissolves. Sodium sulfate dissolves, Na2SO4 dissolves into sodium ions, aqueous, and sulfate ions. Aqueous. All right, I have to balance it with the 2 there. And if I start out, what was the concentration I started out with? Is it 0.001 of that? No. What's it going to be? What's half of that? 0.00050 molar of this. I'm going to get 2 times 0.00050 molar. And get used to writing. Sometimes we'll end up using, I'm using, in standard notation, but a lot of times you have to use numbers that are in scientific notation because they're so small. And 0.00050 molar. In other words, times 10 to the negative something. Many times you have to do that. All right, well, there's your concentration of your sodium ions and your sulfate ions that are floating around in the beaker. What's the concentration of the barium and the chloride ions? Let's write that equation down. BaCl2 solid, actually not really solid, this is a solid, into barium ions and chloride ions. Now, by the way, saw this yesterday with somebody in your class, I think. Maybe somebody in here. Is it going to be Cl2? We're so used to writing. I got you. Last year, I drilled through your skull so many times not to leave it diatomic elements, not to forget to get those 2 there. But you got to remember, this is not a diatomic element. It's not chlorine gas being formed. These are 2 chloride ions, aqueous, being formed, not a chemical chlorine gas. You don't get chlorine gas from salt water. All right, so that guy's balanced, but look at his concentration. It's, again, 0.01 cut in half, 0.00500 molar, 0.00500 molar, and 2 times 0.00500 molar. Now, at this point, I got to look at what my product's going to be. Now, the product is going to be basically either this guy or that guy, right? Okay. Now, so you look up, and you don't have to do this right now because I think I have this one looked up for me. If I look up salt in the back of the book, guess what I'll find? Nothing. KSP for salt doesn't exist because, as you saw in the lab the other day, salt's a very soluble compound. As a matter of fact, I think the KSP we calculated to be like around 20-some, 25. 27. Yeah, 26, 27. I think the actual answer was 28, but still, either way, it's a very highly soluble salt. We're talking about KSPs for guys who are times 10 to -4, -5, -6, or less. All right, so you won't find him there. He is pretty soluble. But you will find a KSP for barium sulfate. That's the guy we're going to have to compare him to. All right, so you'll look up in the back of the book at this point. Although I tell you what, on the test, I think I just give you the KSP. I just tell you the KSP of barium sulfate is whatever. And then you go from there. So you have to write the equation for KSP. All right? So the equation for barium sulfate, I meant. So barium sulfate is the guy I'm actually looking for. He's the one I'm looking to see if a precipitate forms. And his equilibrium expression would look like this. Barium, I think everybody would write this down, plus sulfate, aqueous. All right? Now, in the back of the book, if I look up the KSP of barium sulfate, it's 1.1 times 10 to the -10th. So that's what the KSP equals. All right? Now, what do we have to find? Q. Q is, using these numbers, where exactly does this guy land? Where is he? Is he before or after? Is he going to form precipitate or not? Is he higher or lower than K? The values I will use, the amounts of barium sulfate I have, come from these original 2 equations. The concentration of the barium ion in that beaker is 0.00500 molar. The concentration of the sulfate ion in that beaker is, from this one, 0.00050 molar. All right? So you get the... Now, I'm ignoring these. I don't care about this guy. No, I did. I don't care about that guy. I don't care about that guy because they are soluble. I only care about the ones that are insoluble coming together and possibly forming a precipitate. That's why I chose those 2.
So I'm just recapping. The reason you had to cut the molarities in half is because you doubled the volume. You doubled the volume.
Well, yeah, exactly. I have 100 milliliters of this guy added to 100 milliliters of that guy.
Okay, so
Yeah. And by the way, if you were to do the calculation, which is the next one I'm going to show you, M1 V1 M2 V2, you'd get 0.005, 0.0005. All right. So let's do the Q for this. Q, remember, is just KSP. QSP is KSP, just not necessarily at equilibrium. So it's going to equal barium times sulfate. The equation for the barium sulfate equilibrium expression. And I get my numbers from barium being 0.00500 molar times 0.00050 molar. I mean, this really is fairly easy. It's taken me a while to do it because I'm trying to explain it along the same lines, but basically, this is all you have to do. Get the calculator out, multiply those guys together, and what do you get for Q? You get 2.50? That's 10 to the -6. Now that seems like an awfully small number for Q. However, what did I tell you? If you looked up in the back of the book, KSP is for this guy. I said it was 1.1 times 10 to the negative 10. That's the Qsp, okay? And that's greater than that number. By the way, here's your next mistake you can make. This is a negative 10. 10 and 6, which one's greater? People saying 10's bigger. 10 bigger? Not negative 10, all right? Negative 6 is bigger than negative 10. So is there a precipitate? Yes, there is a precipitate. And you would simply write that down. Yes, there's a precipitate or just precipitate. On a test, on a homework, you might get ones that are no, or there's not precipitate because this number is actually smaller than that one. But in this case, he's larger, so you would see the precipitate. You would see a precipitate out. Now, that one was relatively easy for two reasons. One, I made these values so simple, all you had to do is cut them in half. All right. Two, this equation was not a problem either. There was only barium sulfate. There were no coefficients. I didn't have to worry about something that does become a problem here later. So we'll talk about both of those changes with this next example. Okay, copy this guy down. Both of these things are different in this case. Okay, so this time I'm taking 20 milliliters and adding it to 10 milliliters. So it's not going to be quite as easy as simple cutting in half of the concentration. All right. Also, there's something else later on we'll find is wrong with this one too. It's a problem with this one. But let's take one thing at a time. And we'll start from the beginning. Okay. I'm going to write the equations for the solubility of silver sulfate and sodium phosphate first, like I did last time. Okay. But before I'll start with the equation. You can write this down. Here's Ag2SO4 breaking up. What does he break up into? Ag and SO4. Okay, so Ag, no subscripts, but rather a coefficient. Aqueous plus 1. SO4 aqueous minus 2. You can look at your common ion sheet if you forget the charges or the formulas for some of these ions, but in many cases it's pretty obvious. All right. Here's the first problem. Do not write what I'm about to write down because I want to save you time and I'm going to show you a trick. I could give you even uglier numbers than this and it still could be done this way. Watch. Don't write this down. You should technically have to do this. You should technically have to write out M1, V1, M2, V2, where your initial molarity is this, your initial volume is that. What's your new volume going to be? Is it 10? 30? All right. So you could do that. And you can show me the work for all that. But I'm going to show you a little trick. Basically, I don't have to do all this because if you think about it, let's write out the equation. And again, don't do this on your paper. If I write out this equation, most of the time when you're doing a dilution, you're solving for M2. What's the new volume, the new concentration going to be? So most of the time, what are you doing? You're taking the old molarity and multiplying it by the fraction by which this changes. In the last problem, we took 0.00100 molar, and we would be multiplying it by 100 milliliters over 200 milliliters. 1 over 2, or 1/2, right? That's what you're basically doing. That's why we cut that guy in half and had 0.0005. Okay. Well, I could do the same thing for this. I don't have to write out M1, V1, M2, V2 and do all this work for this when all I'm really doing is multiplying by the volume fraction change, right? The dilution factor, if you want to call it that. So basically, I'm going to take my initial molarity, 0.00150 molar, and multiply him by the factor, the fraction by which it changes, which would be what in this case? 20, right, milliliters? Yeah. Over, not over 10. I knew I'd get that. Over the new volume, which would be 30 milliliters. which makes it a very easy calculation. It's basically times it by 2/3. 2/3 times 0.00150 is what? 0.00100 more. Which makes this guy 2 times 0.00100 molar, and this guy 0.00100 molar. All right. So I'm just showing you and I could have been even uglier, and it would still work. Let's talk about an even uglier situation. Say this was like 37.54 milliliters added to 12.87 milliliters. You can still do the same thing. You take this concentration, 37.54, over the two of them added together, and it's going to do it for you without having to show M1V1, M2V2, the whole 9 yards. Because most of the time when you're doing dilutions, that's what you're doing. You're multiplying by a dilution factor. Okay, so there's your first guy. Now here's your other guy, sodium phosphate. Na3PO4 is breaking up into Na ions, aqueous, plus PO4 ions, aqueous. We've got 3 of them. And look what happens to my concentration. Let's take a look. I made the numbers come out to be okay anyway. 0.0. What am I going to multiply this time to get my initial concentration here? My solubility. 0.00300 molar times what? What over what? Yeah, 10 is the initial amount of this guy, and 30 is still the total volume. So 10 milliliters over 30 milliliters, which gives me what? 0.00100 mole. It makes my life real easy because I made those numbers come out to be, you don't need a calculator to do it, because 0.003 times 1/3 is 0.001. So that means this guy's going to be 3 times 0.00100, and this guy's going to be 0.00100. Now, time to look at what goes on here. Okay, what's happening? And I know a lot of people, as a matter of fact, I want you this time to look it up yourself. Look up in the back of the book and tell me what guy you're looking for. Who am I looking up in the back of the book? I already had somebody last period look up the wrong thing. So if you look it up in the appendix for KSPs, who will you be looking up? Let's take a look.
Yeah, which one is it?
That's what I'm asking. See, I'm not going to be there to tell you. How do you know which one to do? There's 2 possibilities, right? There's this and there's that. When I had somebody look up in the other class, they were looking up this guy or that guy. What are we assuming about these 2 guys? What are we assuming about this guy and this guy if they give them to you? If I'm asking if a precipitate is formed, what has to be the case with both of these guys beforehand, before they mix? They have to be not necessarily saturated. They have to be what? Soluble. They have to be soluble. They can't have a precipitate already. And I had somebody looking up silver sulfate or sodium phosphate. I'm not looking them up. I'm looking up these 2 possibilities. I'm taking 2 clear solutions. I know those 2 guys are not precipitates. I'm looking for whether one of these 2 is. If you look up sodium sulfate, do you find the KSP there? If you look up silver phosphate, do you find the KSP there? Yep. And it's a very small KSP. What is it?
1.3 times 10 to the negative 20.
Yeah, 1 point. Oh, I didn't mean to erase the whole thing. That was stupid. Oh well. Okay. Well, I'm going to write. I'm not going to rewrite all of that, but basically, the guy who I have a KSP for is. That's good. The guy who I have a KSP for is the silver phosphate, right? Yes. So Ag. And you have to write them correctly. +1, because phosphate is a -3. So it's Ag3PO4. He's breaking up into silver ions, aqueous, +1 plus phosphate ions, aqueous, and I have 3 of them. Okay? Now, where do I get my, I didn't really mad that I erased that, because where do I get my concentrations for each of those? I was hoping to write this underneath those. I get them from the ones above. What was the concentration of silver in the equation above?
0.2.
Well, no, 2 times 0.2.
Point what?
0.0022.
0.00200 more. Now, some of you are probably saying to yourself, so do I multiply this by 3? That's a mistake, and it's a very common one. I'll explain why you don't in a minute. By the way, from your phosphate up above, what was that concentration?
0.001.
All right. Now, let me show you. That concentration here, you notice you did multiply it by 2 because it came from what? The silver came from Ag2SO4, so there were twice as many silver ions that the concentration would say. But I do not multiply this by 3 because this concentration of silver didn't come from breaking this guy up. It came from breaking that guy up. So I did multiply it by 2 to get that number. However, because I'm looking for the Ksp, or the Qsp in this case, of this guy, I do use that in the expression. In other words, I am going to have that as an exponent. I just don't multiply it by 3. Okay? All right, so my Qsp is going to be Ag cubed times PO4. So it's going to be 0.00200 molar cubed times 0.00100 molar. Get your calculator out, do all that. You're going to get a very small number, but not small enough. Because remember what the Ksp was for this guy. The Ksp for this guy was very small. So what do you get when you do that?
I got 8 times 10 to the negative 12.
Exactly 8. So 8.00 times 10 to the negative 12th. Is that right? That's what you got for Qsp? If that's the case, you might think to yourself, wow, that's really, really small. It's still bigger than, what did I tell you? What did you guys look it up to be?
1.3 times 10 to the negative 1.
That's the Ksp of this guy. So again, we have a precipitate. Okay? And it would show up as a precipitate. That's what you're going to do tomorrow in the lab. We have a double tomorrow because that's a lab that does take more than one period. All right, not 2 full periods, but we'll take more than 1.